Today's lesson is on the history of the atom. The learning target is I can identify the models of the atom and their respective parts. So here we go. You should be following along in your baby notes. All right. Very first model of the atom goes all the way back to this dude, Democritus. He lived in ancient Greek. He was a philosopher. He kind of just like sat around thinking about stuff because that's the way it worked back in the day. He's sitting there and he's watching a fish swim through a stream. And he thinks if a fish can swim through a stream, that stream cannot just be one unit of water. It has to be teeny tiny little particles of water. He was thinking about like drops of water. So if you can think back to being a little kid at like Chuck E. Cheese or McDonald's playing in the ball pit, Democritus is thinking about a stream and water molecules the same way you and I would think about a ball pit, except the difference between the balls in the ball pit and the atoms or the molecules of water in the stream is that the ball pit is much bigger. So he kind of gets this idea of matter being composed of smaller parts. And then he's thinking about a tree, and I don't know exactly what he's thinking. It's been translated over many, many times. So comes back that he is thinking about a tree, and if he cut the tree and then he cut that chunk of a tree and he cut it again and again and again and again, he'd eventually come to a piece that you couldn't cut anymore. It's elemental piece. He called that atomos, which meant indivisible in some form of Greek, ancient Greece, I don't know, back in the day. And this is where the very first idea of the atom came from. The stuff we see in our lives is made of tinier pieces. Okay. Next, we have John Dalton. John Dalton comes up somewhere in the 1800s. So between John Dalton and Democritus, we're more than 2,000 years apart. All right. John Dalton has this law of definite proportion, and this kind of gave him an idea of how atoms are supposed to look. I'm sorry if you hear the dog going crazy in the back. I just gave him a new toy. Oh, he's prancing. He's cute. I'm sorry. Okay. The model of the atom, he agreed with Democritus that atoms were indivisible. They were made of pieces that could not be broken down further. And then he says all atoms of the same element have the same properties. Essentially, what he's saying here is that all gold atoms look, taste, smell, react like all other atoms of gold. And atoms of gold will never look or behave like atoms of carbon, for instance. So he kind of gets this idea of elements. Prior to this, not prior to Dalton, but kind of before chemistry was a thing, they were thinking that everything was made of some combination of earth, wind, or maybe it's earth, air, fire, and water. So, for instance, a tree is made out of earth and water because you need water to make a tree, right? So we have some people discover some elements, and John Dalton says, okay, these elements, if it's of the same type, they're going to have the same properties. Then he says these elements or these tiny little atoms are going to combine in definite proportion to form compounds. If you think of H2O, it's two H's and one O, right? So I'm going to talk to you about definite proportion. This is definite proportion. He says that H2O is not the same as H4O2. This is because the ratio of H to O in H2O is 2:1. In H4O2, it reduces to 2:1, but it's not really 2:1. It's actually 4:2. So kind of what he's saying is that your subscripts are not reducible, even though these do reduce to the same thing. He says it's not really fair to reduce them because they're not quite the same. He's 100% correct with this. H2O we know is water. H4O2, as far as I know, does not exist. So, you can write stuff down on paper and make it look like it's real, but it's really not. Then we have J.J. Thomson. He comes around a little while later, and he discovers the very first subatomic particle, which is huge. It proved that the atom was not indivisible, but it's actually made of smaller parts. A subatomic particle is underneath, sub is under, like a submarine, it's under the atomic level. So it's even smaller than an atom. And these, the very first particle he discovered was the electron, and he used a cathode ray tube. It's this tube, it's a glass tube that he sucked all of the air out of using like a pump. And they call it a vacuum because you've sucked all of the air out. Inside, or rather outside this cathode, maybe it's inside the tube. I don't honestly know. He's got a positive plate and a negative plate on either side. So they're 180 degrees apart. And he runs a beam through this cathode ray tube, and this beam was attracted towards the positive plate. And if it's attracted to positive, it means it had to be made of negatives. Now, you can't just have a bunch of negatives floating around. If you have a bunch of negatives, they will go looking for positives. For instance, the north end of a magnet is always looking for the south end of a magnet. Sometimes it's not strong enough to find another magnet, but you've seen it where you can hold, maybe you have a super strong magnet kind of close to your fridge, and you can let go of the magnet, and that magnet will stick to the fridge, even though it wasn't touching at first. Thomson kind of imagines this with positives and negatives as well, which is 100% true. So these two ideas together, he puts together what's called the plum pudding model. Plum pudding model is some old nasty food that they used to eat a long time ago, and now I would say it looks like a chocolate chip cookie. So Thomson says that the atom itself is positive, or if you think of a chocolate chip cookie, the dough of a cookie is positive, and your chocolate chips would represent your negative electrons dispersed throughout. And then what happens is that the magnitude or the strength of the positive and the sum of the negative charges are equal in the model. So if I had 12 electrons, 12 negatives, the strength of the positive had to be 12. They have to be matching in magnitude, but opposite in charge. So the magnitude, if I were to tell you, you ask me, I don't know, how tall are you? I would say 5'6". That would be the magnitude because I'm 5 feet 6 inches. If you ask me how much my dog weighs, I would tell you 65 without a unit. That's essentially what magnitude means. If you ask me how much my dog weighs, we can all assume that the units are pounds, so I just tell you the number. That's a magnitude. Okay, next is Rutherford. Rutherford won a Nobel Prize for this. It's a huge thing. It's always on the Regents exam. The model of the atom had to be updated and changed again when he conducted his gold foil experiment. You definitely have a picture of it in front of you, so look at it. He's got a lead box that has some radioactive stuff in it, and he poked a hole in it so the radiation could only escape through the hole, okay? Radiation, in your real life, you can think of it as an X-ray, except this is 1,000 times stronger than an X-ray. Okay, so he puts it in this box. And you know how when you go to the dentist, they put that like smock or apron on you when they take x-rays of your teeth? He did the same thing with a box and put this radioactive stuff in the box so it couldn't get out of the box except where he poked the hole. That's how he gets it to come out in a beam. This beam, the type of radiation coming off of this stuff is called alpha radiation, which is made of smaller alpha particles. Those have a positive charge. Alpha particles are on their way to the sheet of gold foil. As you can see in your picture, the gold foil was wrapped around a detecting screen. The foil was wrapped in a detecting screen. And when the alpha particles hit the detecting screen, it kind of made like a tiny little burn mark. Okay. So, that's not capitalized. That's annoying. I'm fixing that right now. So we have, Rutherford, way back in the day, he doesn't have any type of like special camera that he can take a picture of the detecting screen and the computer just tells him how many dots there are. So this dude had to count them all by hand. Okay. So at the very end of his experiment, after he counted all of those tiny little burn marks, this is what he gets. Most of the alpha particles went straight through the foil, which told him that the atom is mostly empty space. In order for one thing to go through another, it has to be permeable. Because Most of the alpha particles, like 99% of them, went straight through. It had to be that this thing was crazy permeable, almost as permeable as a door frame. You can go straight through a door frame or a doorway because there's no door in it. It's empty space. Okay. Then we have alpha particles that sort of veer off to the side. I'm going to show you what that looks like. Hold on. Google Draw. Let's draw some stuff. We have you like my singing? Can I just nope, I want to draw a thing. Scribble. There we go. Okay, so here is our atom. Okay. Then we have our positive nucleus in the middle. Beautiful. And we have alpha particles. Most of them go straight through. Okay. That's like 99% of them. I'm sorry that this is horrible writing. I'm doing this with my mouse. I didn't really anticipate doing this. So we have 99% that go straight through. Then we have some that kind of come in. We know alpha particles are positive, remember? So it comes in near this nucleus and goes, ew, 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 you're positive, just like me. And it comes out to the side. We'll say that that's 0.9%, okay? So instead of 9 in 100, that's 9 in 1,000. We'll say that, okay? So these are the ones that veer off to the side. When they veer off to the side, that means that something inside the atom had to be positive. The only way it could avoid this atom and go ew, 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 and veer out to the side is if it was avoiding something positive, right? All of these beams in here, these are all positive beams. Give me a line. There we go. Because they're alpha particles. Alpha particles, that's alpha. We got a 4 and a 2. More on this later. Then lastly, we have some that make a major deflection or bounce backwards. That is these guys who, let's make this line red. These go in. This is not making my line red. Hits this nucleus and then bounces back. Okay. Why did that just erase my line? Come on. There we go. Okay, so we have a good chunk of them. Not a good chunk, a very small chunk. 1 in 1,000, we'll say. These guys come in, they hit this nucleus and then bounce backwards. And because this happened such a small percentage of the time, Rutherford knew that whatever this positive thing that was in there, it was super, super, super small. Okay? That's Rutherford. Then we have the Bohr model. The Bohr model, Niels Bohr, he's a quantum chemist. My dog's throwing a tantrum. He had some math that he was thinking of. Oh, can we just clear everything? Is that an option? Oh boy. No. Give me this. There we go. Okay. So Bohr did some math and figured out that these electrons, if you look at your Rutherford diagram, Rutherford kind of has them just like scattered all over the place. Bohr says, you know what? These electrons are negative. The nucleus is positive. These guys are probably going to attract each other. So the electrons are going to wind up stuck inside the nucleus. They're going to, like magnets, they're going to stick. But if Rutherford is finding a positive piece that's going to kind of like hang out in the middle like this, those electrons that he drew in here, can I get rid of these lines now? Let's, if he has electrons just like dispersed in here, oh, I have to click every time for a new, okay, let's just copy and paste. Oh, no, stop that. If we had electrons just dispersed all over the place and we knew these were negative, they're eventually going to find their way in here. And then these deflections are not going to happen because this won't be a net positive. It'll be a net neutral because your positives and negatives are going to cancel out. Okay. So Bohr goes, the only way to get these electrons to kind of stay in place is to lock them into orbits the same way the planets orbit the sun. So he took these guys and put them inside of orbits. I'll show you the slide again in a minute. Oh, I don't want a circle. I want a ring. Let's make that empty. Beautiful. Okay. So now this is the Bohr model. Okay. He takes all of these electrons and locks them into orbits, unlike the planets that have just one planet per orbit. He's putting in a few. He did some math to figure out the numbers. He called this the planetary model because the the electrons circled the nucleus just like the planets circle around the sun. So he calls them orbitals, and they each have their own specific amount of energy. So my dog is just running across the room. He's crazy. Okay, I'm sorry. So he says that each of these electrons has their own specific amount of energy. He called them quanta. So if you were to take, let's say, give me the scribble. And let's say I heated this up. This is fire, okay? Let's make it orange so it looks like fire, okay? If you heated this up, oh my God. Cooper, stop that. Do not. You heat this up, this electron, nope, just this electron. This electron gets like wiggly, and then it's going to jump up to higher energy levels, okay? This is called the excited state. This can't stay here forever because these other electrons are going to repel it. They say, ew, get out of here. You're negative. There's not enough room for you. Plus, this is sort of attracted to the positive of this nucleus. So it kind of jumps back to where it belongs. That's called the ground state. Okay. So according to Bohr, when an electron gained enough energy, it could temporarily, very important, jump to a higher energy level. He'd call that the excited state. Then when they moved back to their normal state, he called it the ground state. Okay. More on this later, pinky promise. So as the electrons do this, they release energy in the form of light. So I probably showed your class the colored fire in the Bunsen burner. That colored fire is based on this Bohr model science. Okay. So when the electrons come back to where they belong, that's when we get the cool light. Now, each of the elements creates unique spectral lines based on their electron movement. So there's a picture of it in your notebook. It kind of just looks like a black bar. And there's 3, maybe 4 vertical lines in it. Those lines are specific to hydrogen. Hydrogen is the only element that gives off those specific lines. All 118 elements have their own special set of lines. It's kind of like their DNA. And we can use that to identify elements. That is how we know that it rains diamonds on most of the outer planets. That's because their atmospheres are made out of methane. Squish carbon enough in a high pressure situation, it's going to turn into a diamond. Okay. Any of you become millionaires, billionaires, trillionaires, remember me, your awesome chemistry teacher, and go buy me some like Neptunian diamond. Okay. You'll be my favorite kid ever. We can also use spectral lines to identify elements in stars. It's how we know that the sun is made out of hydrogen and helium. So Bohr is really cool. We'll do more on him a little bit later. Okay. The very last model is called the wave mechanical model. It's also sometimes called the modern model, the electron cloud model, the quantum mechanical model. It kind of depends on who you talk to. Okay. I like wave mechanical only because that's what the Regents calls it. I don't have a preference, honestly. But in this, we're looking at the Bohr model, and we have a bunch of scientists do this. It's not really credited to one single person, but we have the electron now mathematically fits the bill better for some crossover between matter and energy. Okay. That sounds crazy. As electrons move around the nucleus, right, they're orbiting. Just imagine this orbiting. Okay. It's orbiting. When this one moves to 6 o'clock, this one's going to move to 12 o'clock because these guys are repelling each other. This one moves. Oops, that's not what I wanted. I should be better at this. This moves to 9 o'clock. This one's going to move to 3 o'clock because they're repelling each other. Okay. So kind of what happens, is there like a spray paint option? That would be really cool. I don't think I have that. This is not Paint. This is Google Draw. Clearly not as good. So what happens is that instead of these being like specific orbits, we kind of call them clouds. And the reason for this is because the electron's going to follow this like wiggly, wobbly path because it's a cross between matter and energy. So this little baby electron is going to like follow this loop-de-loop. And there's going to be some areas where we're definitely going to find an electron, like this area, for instance. But this electron might only be in this area a small percentage of the time. You see how there's like hardly any wiggles over here? This is because it's a cross between matter and energy. The guy who came up with this is named Heisenberg. Unfortunately, I don't remember his first name. It will come to me at some point. But he called this the uncertainty principle. And it kind of comes down to the fact that electrons move so quickly around the nucleus that we can't know exactly where they are. If I learned how to do it, or actually relearned how to do it, I wanted to know, for instance, where Jupiter was going to be on May 15th, 4038. I would be able to do some math and figure out the exact celestial coordinates for what I say, Jupiter, for Jupiter on that date and time, because the patterns are very predictable. Electrons, not so much. They're not predictable. So we call it the uncertainty principle. We kind of have an idea of where they're going to be, but not exactly. So this forced the orbitals to be renamed clouds. If you look up at the sky, some clouds you can see definitively where the edge is. Other clouds, they're so wispy or so far away, you have no idea where it starts and where it ends, where one cloud begins and the next one ends, right? So that's why orbitals were renamed clouds. All of this comes down to probability and math and calculus and a bunch of boring stuff. So we have some more dense areas of the cloud is where we're more likely to find an electron. So if I colored in this area quite a bit, right on that like original circle I had. Okay, move the clicker. Click on this. Boom. You see how there's like a dense circle here and then it gets a little looser out here? So this would be a low density area or a low probability area where this dark region very close to the initial line is going to be a high probability area. So the electron is not really going to follow a nice circle or a nice ellipse. It's going to kind of like wobble back and forth. So it's going to be a little closer to the nucleus, then a little further, then a little closer again. But it spends most of the time in this dark region. Okay. I hope that makes sense. So that's what all this comes down to. All of this is based on math. It is not logical arguments. Some of these equations are super difficult. Some of these equations, I think it's a Schrodinger equation, only works for one electron. And once you start adding in extra electrons, the math gets so crazy that we just can't solve it. We're getting there every single year. We get closer. This is why we teach you science, so that you can teach the old people some new stuff, because you guys are going to have some great ideas. Okay, so that's everything on the history of the atom. Essentially, what it comes down to is that the model of the atom, the model that we draw, has changed over time. And all of these guys built on the idea of the one before them, except Democritus. He kind of came up, maybe he stole it from somebody else who just didn't know how to read or write. Who knows? John Dalton built off of Democritus, and Thompson built off of Dalton, and Rutherford built off Thomson. They're all building on the guys before them. So if you think of this like a cell phone or an iPhone, for instance, the very first cell phone was a disgusting beige brick. And now we have the iPhone 11 with, I don't even know how many cameras are in it. It's incredible. It's a computer in your pocket. We had to develop technology in order to get a better cell phone. These guys had to develop more and more technology in order to get a better understanding of the atom. That's it. The atom has been the same the whole time. We just can't see it. So we have to come up with all of these like thought arguments and all these experiments to kind of give us a picture. It's almost like I put a mystery item in a box, and the first thing I tell you is that you can put your nose in the box and you can smell it. And then I tell you that you can put your foot in the box and you can feel it with your foot. And then you can feel it, but only one hand at a time. Every single time you are gaining more information because you're getting a better understanding of what's in the box. So that's what's happening with this atom. The atom itself has not changed. We are just changing the picture based on more information. So if you got any questions, I am doing a full-on lecture video for Rutherford and for Bohr, and that's it. So if those are the two that you're confused about, give it another day or so. If it's any of the others, go back and rewatch the video because you